Back. Almost to the end. A few more videos. Today's video is about random variables and the expected value of those random variables. It's going to feel like a quantum leap in the sense of we're abstracting from what we discussed before. Right? Basically, a random variable is a way to take a bunch of outcomes from a sample space and categorize them. Right? We're going to assign each one of them a number, and by doing that, it's going to allow me to put these events and these outcomes into groups. And once I can analyze how the groups behave and what the probability of landing in each group is, that's going to allow me to take what might be a really big tree or a really big set of outcomes and bring it back down to a more manageable level. We introduced a new notation for this. Random variables are usually written as capital letters. And so in my text here, I've got the probability of capital X equals 2. And so that's a notation that you'll see sometimes. That is the probability that this random variable is equal to 2. And what that means is, what is the probability that I get one of the outcomes which this random variable assigns to the number 2? Right? Again, it's a mouthful when you say it all, right? But that's sort of the abstraction that's going on. And so this probability statement is papering over a more fundamental probability statement, but it's one that will give us outcomes that are easier to manage, easier to count, easier to calculate with. And so I can just say, well, what's the probability that X equals 2? Rather than saying, well, let me take all these outcomes which might have something in common, which I assigned the number 2, and let me add together all those different possibilities and all those probabilities. We use random variables a lot when we're counting things. Like, for example, if we're counting the number of heads or tails, like we're about to do in the table below. This will be something that a random variable is easily measured with. But it's mainly about having these groups, right? If I assigned a different number to every single outcome, then a random variable is not really that useful, in the sense that it doesn't help me group these things together, right? I'll show you what I mean in this tree. I mean, this is the tree drawn out for the experiment where I flip 3 coins, right? Rather than do H1, T1, H2, T2, remember when I was doing the numbers down below before with the cookies? Rather than do that, what I'll do is I'll list the individual coin flips in the final outcome. So for example, in this top path of the tree, this outcome I might measure as heads, heads, heads. And I would notate that as heads, heads, heads. And if I gave all of these branches a standard 1/2, 1/2, then that would be 1/2 times 1/2 times 1/2. The probability that we achieve this outcome is 1/8. 1/2 times 1/2 times 1/2. Of course, it would basically be the same, only I might have heads, heads, tails now. The probability that the outcome I look at after 3 coins is heads, heads, tails is also 1/8. Again, every path in this tree has a 1/2 probability or conditional probability assigned to it. And so all of the calculations will be 1/2 times 1/2 times 1/2. Probability of heads, tails, heads, 1/8. And I'm just going to skip ahead to the end now because I don't want to make you watch me write all 8 of these. The probability of tails, tails, tails is 1/8. All 8 possibilities, all 8 outcomes in this sample space, flipping 3 coins. Again, all 8 of these outcomes are equally likely, 1/8. But just because they're all equally likely and they add together to be 1 like it should be, doesn't mean that from the outsider's perspective, I would consider all of these outcomes the same. And for example, if I just flipped 3 coins and I didn't stamp a number or a serial number on each one of them, how could I tell the difference between this outcome and this outcome? Okay. In one of them, I have heads, heads, tails. The other one, I have tails, heads, heads. Unless I specifically set up my experiment to flip the coins one at a time, and I could keep track of which one was first, which one was second, and which one was third, these two outcomes would be the same to me. Right? If I just flipped 3 coins in a box, right, then, and I'm not keeping track of each one separately, then these two outcomes would be the same to me. And so if I'm more concerned with, for example, in this case, how many heads or how many tails are in my outcome and not specifically which order they appeared, I need to start grouping these outcomes together. And that's what a random variable lets me do. I'm going to come up with a new random variable called capital X. Random variables usually get capital letters assigned to them. And each one of these outcomes will be assigned a number. In this case, what I'll do is I'll call this the number of heads variable. So in this first outcome, heads, 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 the random variable X would assign the number 3. There are 3 heads. And so forth down the line, 2, 2, 1, 2, 1, 1, 0. So this is the random variable called X. And now I notice that there are different numbers of outcomes in each category. How many categories do I have? Well, I have a 0, I have a 1, but that appears in more than one outcome. I have a 2, that also appears in more than one outcome. And I have a 3. And so there are 4 different values this random variable can take. And these are not equally likely. Even though each of the outcomes is 1/8 equally likely to appear, the values of the random variable are not equally likely to appear. We'll talk about that in just a moment. Because the random variable different outcomes are not necessarily equally likely, it's not really appropriate to do the same kind of counting blank over blank that we used to for sample spaces. So we need to come up with a new tool to measure, well, given our random variable, what is the probability that it takes on each of the values which it's possible to take on? Such a table is called the probability distribution, or PD, of that random variable. A PD can be really short, right? If, for example, if up above when we had this random variable, if I were to make its probability distribution, I would say the different values of X are 0, 1, 2, and 3. And in this table, I would also need to keep track of what is the probability that that X value appears. So sometimes that's labeled as P of big X equals little x. I'm not a huge fan of that. I think it is pretty direct though. What's the probability that this random variable takes on this specific value? Well, let's see. We know all of these outcomes are 1/8 likely, so we can just count. How many outcomes are assigned to the number 0? Just 1. So that's 1/8. There's only one outcome, and that's a total probability of 1/8. How many outcomes are assigned to the number 1? It's 1, 2, 3 different outcomes. Each one of them is 1/8. So that would be 3/8 likely in total for all 3. Okay, how many are assigned to the number 2? 1, 2, 3 outcomes. So that's 3/8 likely. And the number 3 is 1/8 likely. And so in this table, we have fully measured what is the probability that this random variable takes on its specific values. And even though the underlying tree is equally likely, everything is 1/8 likely to appear, because we've grouped these outcomes in a different way, we've grouped them by the number of heads, that grouping is inherently not equal anymore. You can see that it's 3 times more likely to have 1 heads or 2 heads than it is to have 0 heads or 3 heads. This is the probability distribution of the random variable x. And we'll see some more examples and we scroll back down. Okay, I've scrolled back down and I've put a table in my notes here. And this is a kind of a generic probability distribution, right? They didn't even give it a name when I copied this off of my Open Math. So I had to go in and give it a name. I gave it a name, capital X. But in this table, there are lots of different outcomes. 1, 2, 3, 4, 5, 6, 7 different possible outcomes. And their probabilities are listed on the left. Well, just like any other probability, right, probability must be between 0 and 1. And just like before, if I added together all of the outcomes, I should arrive at a total probability of 1. Right? That captures all of the outcomes of the experiment in the sample space. Same thing here in the probability distribution. If I added together all of these numbers, I should get a total of 1. Let's see if I do that. 35%, 40, 45, 50, 60, 75, 85, 95, 100% total, or a sum or a total of 1. So this table would represent a probability distribution of this random variable. I'll always check. Chances are if it doesn't equal 1, you've missed a counting somewhere. You've left one of your outcomes out of the table. But in a pinch, right, if you absolutely have triple, double, sextuple checked all of your work, and you're sure that all of these are correct, and at least the ratios between them are correct, you can fix them. I'd say, for example, if I added all this together and I got 0.9, and for some reason I was 190 million% sure that this is the correct table, I have not missed anything, and even though the overwhelming evidence says you're likely to have missed something, well, take all the numbers in your table and divide them by 0.9. And that would fix it. We shouldn't see too many examples like that, right? Everything in this class should be already set up for you in such a way that when you correctly calculate the probabilities, they will add to 1. And when you make your probability distributions, they should always add to 1. So why do we even talk about random variables? We saw before that random variables were nice in the sense that they allowed us to group these outcomes together, but there has to be a more compelling reason than that, a more mathematical reason than that. One of the things we do with random variables is we talk about their expected value. Right? The probability distributions that we saw up above, you saw that table had 7 different rows in it. And each one of those things was slightly different in the probability column. That means they're not all the same likelihood. And so if I ran that experiment, I could get several different outcomes with several different probabilities for each. And that's a lot of information to take in at one time. To summarize that information, right, I will talk about the random variable's expected value, or EV, expected value. Basically what that is just an average. Right? But it's not the same kind of average like add them all up and divide by n, right? That would be the average that you might do, right, if you were calculating what your homework average is in this class. Take all of your grades, you add them up, and you divide by how many grades there are. We do that in the exam category for our class. Now this average, I would like a weighted average. That is, I want some things to be weighted more heavily than others. A weighted average is what we use to calculate the final grades in this class, right? The homework grade is about 20%, and all of the test grades together are about 50%, and the final exam itself is 30%. Right? So some grades are more important than others. That's why students sometimes will say, oh, well, I got really good grades on all my homework. I got hundreds on those homeworks, but I didn't get the grade that I wanted out of the class because my exam grades were a little bit lower than I thought they should be. So because the exam grades were worth more in the average, their weight was higher. And I'd like to do the same thing here with random variables. I want to weight them by the probabilities that they occurred. I'm going to scroll back up to the previous example. Essentially what that means is before I add together all of these things, what I'm going to do is I'm going to multiply them together. Right? Whereas a weighted average, you might be thinking, well, if something is twice as more likely, then I'm going to multiply it times 2. Right? That might feel right when it comes to a basic weighted average. But the nice part about the probability is that because the probability is already guaranteed to sum to 1, I'm going to multiply all of my outcomes times the probability that they occur. And that's going to take care of a lot of mathematical details for me. And so in my formula, what you'll see is I'm going to take every outcome, call it little x, I'm going to multiply it times the probability that that outcome occurs. Probability. I'll do a capital P since that's what I did on the previous table. And I need to add all of these things together. I'm going to use a special symbol to show that. This symbol is called a sigma. You might have even seen one of these before. It's a capital Greek letter sigma. And in math terms, when you see a sigma, that just means add them all together. Right? You might have seen it with additional numbers right up above them or below them. And if you were in a pre-calculus class, you might have seen them that way. We're using this in a very informal sense. Right? So informally, sigma x times p of x means multiply them all together and then just add them all up at the end. And so that allows me to show the adding part of the formula without doing plus, 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 and keep on making it longer and longer. Because I don't know how many outcomes there are in this random variable. If there's only 3 outcomes, then I only need to add 3 of these together. But if there are 200 outcomes, I need to add 200 of them together. Before we look at an example from the homework, or another example from the homework, let me take this random variable from before, and let me find its expected value. I know the expected value of this random variable is the sum of all of its values multiplied times the probability that those values would occur. I'm going to have to do the legwork here. So that's 0.05 times 1 plus 0.1 times 2 plus, you can see what I'm doing here. I'm just going to go ahead and skip ahead to the end. Plus 0.35 times 13. Right? I've multiplied all of the values times their probability, and now I'm just going to go to the calculator and ask it to add all of these things together. That equals 8.3 by my calculation. Leo, let me know if that's correct or incorrect, but I think that's about right. And what that means, right, this expected value is that is the average value of the number that I would expect this random variable to assign. Notice that this expected value, 8.3, is not one of the specific numbers in the table. Right? That's going to happen more often than not. The expected value is not one of the actual values that the random variable can give you. Rather, you can think of this as a long-term average value. If I kept track of all the different numbers that this random variable were to give me and average all of them, then, if I did this a very large number of times, then this is about the number I would expect to come out of that average. Although we're going to see with an Excel spreadsheet on the next example that even what we might think is a large number, several hundred, that's really not enough to make this a guarantee that it's pretty close to this average. But in general, what we say is that if we run this experiment, this is about the average value I might expect to get, 8.3. Sometimes it's higher than that, sometimes it's lower than that. This is just the expected average. That brings us to our final example. This is one of the word problems from the homework. And let's give it a read. So we've got a game here, and there is a probability of winning and losing. And it's talking about winning and as well as net gain. That's going to be important because when we set up our random variable, if we want our random variable to measure how much we win or lose, right, on the net scale, right, how much money do we have in our pocket at the end, then we probably need to calculate the net gain or net loss. Because this is a game which costs a certain amount to play, even if you win, right? Even if you lose, you pay the same $5, right? And then, so we'll keep track of the net gain and the net loss to keep track of how much money I should expect to win or lose every time I play the game. And because if the game has an expected value of $4, that's great. But if I have to pay $5 to play it, that doesn't make any sense, right? So we'll keep track of the net as far as our random variable. So let's set this up. See, call our random variable x, and it says the probability that we win is 0.04, and the net gain was $9 in that situation, plus 9 in this case. So with a 4% chance, I'll end up $9 ahead, but that means there's a 96% chance that I'll lose. And if I lose, then I lose the money that I put up to play the game, minus $5. So this is a game which only has two states. You either win or you lose, right? But that's pretty much the case for all gambling type games. Right? Not every gambling type game will have the same probability or the same net gain and net loss, but I can use my expected value formula to calculate the expected value. So I know that I'll add together every value times the probability that that value occurs. In this case, it's not so bad. 9 times 0.04 plus negative 5 times 0.96. I'll type that into my calculator. It shows negative 4.44. I'm going to round that to 2 decimal places since we're talking about money in this case. And the way I would interpret this is by saying, well, I expect to lose $4.44 every time I play this game. Yes, I could win. I could win kind of big, right? $9 is almost twice as much as I paid to enter this game. But at the same time, the likelihood of winning is not big enough to overpower that overwhelming chance of losing here, right? If this were a real game that I were playing, I would make the payout much higher, right? Because if you think about it, if you only win 4 times out of 100, and you lose 96 times out of 100, seems like the jackpot would be much higher, right? Otherwise, right, it's too clearly a losing game, I think. Right? Most games of chance, most casino games, right, they're not such clearly losing games. But in this case, again, the random values on our homework have picked these. So I would expect to lose $4.44 every time I play this game, minus 4.44. If I played this game many, many times, I would very much expect to come out behind, not ahead. It's certainly possible that it could happen, right? I could be on a winning streak, just like anyone that goes to the casino could be on a winning streak. but it's very unlikely. Even if I have a positive expected value, which by the way will never happen if you're talking about a real casino game, that doesn't guarantee that I'll have a win. But a negative expected value, right, especially these kinds, right, in the long run, definitely I would expect to come out behind. Let's take a look. I made actually a Excel spreadsheet to model this situation. Let me switch over to my full screen here. There we go. So what I did in this Excel spreadsheet was I basically modeled the game. You see, every here will be how much money I have in my pocket. I'm going to play this game repeatedly. And I get to change the numbers. So basically, I allowed myself to control for the random numbers that my open math would have given me. So if we have a $9 net gain from winning, you can see here the chart has already populated. But this is not taking into account all the money I get from losing. So it looks like 1, 2, 3, 4, 5. There's 5 wins. This chart represents 200 simulated games. I can click my calculator button here to redo it. You can see this one, has even more games. Right? So over the course of 200 games, it looks like I'd win somewhere 63, 45, 72. So I might have between 3 and 10 wins over 200 games. But now let's bring in the net loss. -5. Oh my goodness. So bringing in the net loss clearly shows here, wow, this is really not a winning game. Even if I click my calculator button lots and lots of times, after 200 runs, this number measures how much money I will win or lose total after playing 200 times. And that number looks to be getting on there almost -1,000. Sometimes a little bit less. No matter how many times I click the calculator button, I'm not getting a very good result. I'm definitely not getting anywhere close to the positive side of the chart. Every now and again, I will have a few positive values. You can see if I just so happen to win the first game, I'll be positive for a while. I'm not sure if I'll ever get one where I win the first 2 games in a row. It is possible, it's not very likely. And it's a 4% chance that you win the first game and a 4% chance you win the second game. Well, that would be 4% times 4%. That would be 0.16%. Yeah, 0.16%. That is 16 times out of 10,000 that I win the first 2 games in a row. So there's another one where I won the first game, not the second. And I'm not going to waste your time trying to click to find it because it's such an unlikely result. The interesting part about this Excel spreadsheet that I've set up is that not only can I simulate 200 games and see the cumulative effect, but I can also do an estimation of the expected value. Here's the expected value we calculated, -4.44. But after 200 runs, I can give you an estimate of the expected value here. Now, it just so happened that this expected value was exactly -4.44. But because of the randomness involved, that can change a little bit. You see how every time I click the calculator button to rerun my experiment, this expected value changes a little bit. Never that far from -4.44, but still never exactly 4.44. Oh, there's one that's exactly 4.44. Sometimes you just get lucky, right? But I'm never too far away from it. That's just the randomness for it. Anyway, this is a really cool spreadsheet. If you wanted to play with one like this, you can send me an email. I'll send you this spreadsheet, or I'll show you how you can make one of your own. It's not a super complicated Excel spreadsheet to set up. This, by the way, is why you won't see a whole lot of math professors in the casinos, right? Because we do this for a living and for a sense, right? And so when we go to the casinos, it's like going to the movies. It's a nice time. Spend $50, have some drinks, and then we'll walk out $50 in the hall, saying, "Hey, that was fun." Anyway, this is neat stuff. Anyway, I don't want to take too much of your time. This has been expected value as well as random variables. I'll see you next week.